So we have acetic acid is a weak monoprotic acid with Ka 1.77 times 10 to the negative fifth. Solid NaOH was gradually added to 1 liter of 0.0179 molar acetic acid. Assume no volume change occurs. So that's a very important statement. Normally, when we're adding a certain milliliter amount of our base, which is the questions we went over last week, we were adding a milliliter amount. What that meant was we couldn't work in concentrations. We had to convert everything to moles, and then we had to change the volume by adding the volume that was added to the original volume, and then finding the new molarity in order to find our pH, our POH, concentration of hydrogen, whatever we needed to find. So we need to kind of go back and forth. In this case, we're adding a solid, and we're assuming there's no volume change, which means we don't have to work with molarity. Well, we do have to work with some molarity, but we're giving it more straightforward because we have moles already. We don't have to figure out the moles for a specific milliliter amount of base. So let's begin. The first part of the question, calculate the pH of the solution after the addition of 0.0107 moles of NaOH. Okay, so we have this amount of acetic acid, right? The best thing to do, and just to reiterate on the concept of an acid-base titration. So we're adding a base, and we have the equivalence point, the pH is going up. In the beginning part, before the equivalence point happens, we can consider this a buffer, because what's happening is you're having your weak acid, and it's dissociating into your conjugate base plus some amount of hydrogen. So you're going to have a ratio of your conjugate base to your conjugate acid. And this is perfect for the Henderson-Hasselbeck equation, where pH equals pKa plus the log of base over acid, meaning the conjugate base over the weak acid. Then when you get to the equivalence point, you have to use the Kb, because I'll put Kb here. The reason why is because at the equivalence point, the definition means that all of this HA was converted to our conjugate base, meaning the only thing present in our solution, with the addition of, you have some sodium ions, you have hydrogen ions, but you no longer have the original weak acid. You only have the conjugate base, you have hydroxide, and you have sodium, and you have H+. So what that means is that the association, or the production, this is a better word, the production of hydroxide ions from the reaction of this weak, or of this conjugate base, will be the main cause of the pH, or the main determinant of the pH. So what you would do is you would have your weak base, or your conjugate base, you're adding it to the water, and then there's going to be some equilibrium that occurs, which reforms your acid. And then you're going to have OH minus. Your job is to use an ice chart to find this OH minus concentration at equilibrium using the Kb in order to solve for your POH and then your pH. Then after the reason why the pH changes is because you're adding an excess of base. So all you would have to do is figure out the mole difference between your base and your starting acid. That difference and that excess amount of NaOH is going to be directly corresponding to the POH. So let's say if we have 2 moles of acid, or sorry, 2 moles of base, and you started out with 1 mole of weak acid, then the excess NaOH is going to be 1 mole, which would then be directly used to find the POH and the pH, right? So you would do negative log of this, 14 minus negative log of this equals pH. But so assuming it's a very good question, because that's where some students get confused, is that, wait, why are we now trying to neutralize all of the acid? Because isn't it a weak acid? Doesn't it not need to be neutralized? But no, it all needs to be neutralized, but by itself, a very, very small percent of it neutralizes. And the base is there to neutralize the rest. And also, Brian, in this case, how would we calculate the initial pH? So initial pH is very easy by using an ice chart. by just, and let's do that first. Let's do the initial pH. I like how this lesson, this question is diverging. We didn't even start it yet, and we're not going to. So let's see. Acetic acid. Let's write the formula for it. HC2H3O2 plus water yields C2H3O2 minus plus H3O plus. Okay, now our initial concentration is 0.017. So here we go. I'm going to do ICE, and we're going to have our initial concentration 0.0179, 0, 0, 0. This doesn't count because it's pure liquid, minus X plus X plus X, X, X. You get the gist right now, 0.0179 minus X. All right. Then we can do X squared over 0.0179 minus X equals 1.77 times 10 to the negative fifth equals the Ka, right? This is the expression for Ka. Now we're going to solve for X. But since the initial concentration, the 0.0179 is 10 to the negative 2, and the Ka is 10 to the negative fifth, that is a 1,000-fold difference. So again, on the cusp, but this is a 1,000-fold difference, meaning the ratio is large enough where we can ignore this X. And if you don't ignore the X, you'll get a pH that is very, very close, 0.01, within the tolerance of 0.01. Okay, so we can solve for this, and I can do that right now, or maybe you guys can help me. We can solve for can anyone give me the answer what X is? Because it'll be the square root of 1.77 times 10 to the negative fifth times 0.0179 underneath the square root. And what does that equal? All right, 0.00056. All right, that sounds right. So 5.6 times 10 to the negative fourth. Okay, now that sounds right. It's a hydrogen concentration, and it's greater than 10 to the negative 8, meaning it's an acidic. And that makes sense because it's acetic acid. So what we can do, since this equilibrium concentration represents the H3O plus, so we can do the negative log of that to give us our pH. And what is our pH then? .25, and that's great. That makes sense because it's a weak base. 3.25 as our initial pH. Okay, are there any questions on that? All right, and then for an aside, I will say this. So last week, not to put you on the spot, Christina, but you made the great point of, wait a minute, when we have acetic acid or any weak acid, we have an initial amount of dissociation that gives us this pH. Don't we have to count in that the number of effective, or the number of, let's say this, the number of active weak acid particles is now decreased because an initial amount of them are converted to conjugate base? So only less than 0.0179 molar needs to be neutralized. Technically, yes. But you can try this on your own. And I did try it when I went home for both examples that we talked about in class. And it turns out they're very, and as I expected, they are extremely similar, off by 0.001 pH units. So that is the absolute correct approach. But the numbers are small enough and the differences are large enough that we can assume otherwise. We can assume that every acid mole that needs to be neutralized by the added base. Very good point, though. I just want to bring that up in case other students were confused about that or thinking about it over the long weekend. All right, so now I'm going to erase. There we go, perfect. All right, now let's go on to part A. Finally, calculate the pH of the solution after the addition of 0.0107 moles of NaOH. All right, So we have this amount of acetic acid. We first need to find out the moles. So we have 0.0179 molarity equals X moles over 1. And you can just solve that very easily. And we have 0.0179 moles. So this is the amount of moles that needs to be neutralized in this titration. So you have that many moles of, I'll just put HA. That's the weak acid. So let's write the equation. And we'll call acetic acid HA. I don't feel like writing it every time. And we'll call acetate A minus. So you have HA plus water yields A minus, that's not a minus, A minus plus H3O plus. And for now, we're going to write the moles because we're going to use the moles. We want to see how many moles are neutralized. And we're not going to really do an ice chart here. We don't have to, but we can basically figure out what's going on. So it's important to write the equation, but we don't have to use it every single time. We can use it for B. We'll have to do an ice chart. So let's talk about it conceptually, that we have this many moles. We are adding how many moles? 0.0107. So that means the strong base, because it is a strong base, every one of those moles that are added will neutralize that many moles of acid. So if we subtract these two, that will give us the total number of moles of acid remaining. So can anyone do that math for me? We're taking the acid moles, subtracting the strong base added moles in order to get the amount of acid remaining. 0.0072. Good. 0.0072. That is the moles of HA remaining. Okay. Now, how many moles are neutralized then? Meaning, how many moles go from HA to A minus? Good, exactly, 0.0107, the exact amount of strong base that was added. So now we have 0.0107 moles of A minus produced, not remaining, produced. So that means we can use the Henderson-Hasselbeck equation because we have the moles, which can convert to molarities very easily. We have 1 liter and there's no volume change. So it's the same as the molarity. And we can figure out the pH. So let's write it in the equation. And I want your guys' help. So pH equals pKa, which is 1.77 times 10 to the negative 5th plus the log of the base, which is the conjugate base that is now produced, which is 0.0107 molar, because this is divided by 1, this is divided by 1, over the acid remaining, which is 0.0072 molar. And whatever this is would yield us the pH. And you can help me calculate that. And we have an answer already, I think. Oh, whoops, my bad. You're right, you're right. Yeah, so, okay, I'm ahead of myself. So we had to take the negative log of this to find the pKa. My bad. Usually they give me pKa, whatever. But okay, so negative log of that plus the log of the ratio. And we got 4.75, and also Sumi had a question. The concentrations we're using in the Henderson-Hasselbeck, which is a very good question, by the way, is the weak baser acid and its conjugate baser acid that's converted. So we can't use, let's say, NaOH and the acetic acid. We can only use the conjugates of each other. That's why we can only use it before it's neutralized. So we do have a ratio. Once all of the acid is gone, we'll have a ratio with 0 on the bottom, and we can't have that. Oh, okay, the pKa is 4.75. All right, so then this could be 4.75 plus the log of 0.0107 divided by 0.0072. And what does this equal? It's going to be 4.92 by consensus. All right, let's move on for time's sake. Let's move on to the next one. I'll circle all of this stuff. Delete. All right, now part B. So now what is the pH of the solution after the addition of 0.0179 moles of NaOH? Well, that number looks familiar. That's the same amount of moles that we have of acetic acid. So that means, if we're looking at the equation, that means that every single mole of HA has been converted to A minus, because we now, the moles of the acetic acid and will be neutralized by the moles of the NaOH. So what does that mean? That means all of the moles are going to be in the conjugate base. So we're going to have the conjugate base concentration is going to be 0.0179 molar, because we assume there's no concentration. We assume there's no volume change. Sorry. There's going to be one sloppy video to edit. Okay. Now that we have this as the conjugate base, remember what I said about the equivalence point, because now we reach the equivalence point, meaning all of the strong base has neutralized the weak acid and turned it into its conjugate base. We need the Kb. So the Kb is going to help us to see what is the effective hydroxide concentration that this conjugate base produces. So the way we do the Kb is we do 10 to the negative 14th divided by the Ka, which is 1.77. Oh, too many ones. 1.77 times 10 to the negative 5th. And can anyone give me the answer for that? Exactly, Sumi. Yep, Kw over Ka. So who wants to give me the answer for the Kb? This is going to be equal to Kb, which we have, good, 5.64, 10 to negative 10. Sounds right. 5.64, 10 to the negative 10. All right, that's pretty small. That means this is going to be a relatively weak base. So the pH will be around 7 something, maybe 8, but not much higher than that. All right, so because we have this Kb, we need to use the ice chart to write our dissociation of the base. I mean, not dissociation, our hydroxide production caused by the base, which will be, all right, A minus plus H2O yields HA plus OH minus. That's what the Kb represents. Our A minus concentration we know as 0.0179. Water's nothing. We have 0 here, 0 here. We have plus X. We know how this works. Yada, yada. Minus X. 0.0179 minus X. X squared divided by 0.0179 minus X equals our Kb, 5.64 times 10 to the negative 10. And in this case, especially because our Kb is so low, we can neglect X in the minus X part. So does anyone want to solve X for me? And then it'll be the square root of 5.64 times 10 to the negative 10 times 0.0179. Ding, 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 we have an answer. 3.18, 10 to the negative 6. Looks good to me. 3.18, 10 to the negative 6. All right, now this concentration represents X, which is at equilibrium after the equivalence point, or at the equivalence point, is our hydroxide concentration. So using our definitions of the negative log of the hydroxide concentration, we can find the POH. So we can do POH equals negative LOG of 3.18, 10 to the negative 6. And then from there, once we solve that, we can do 14 minus the POH is going to equal our pH, which will equal what? So can someone tell me the POH? And then can someone else tell me the pH? So POH equals 5.5. I assume that is the POH. And then the pH would be 14 minus that, which would be, I could do math, 7.5. 8.5, yes. That's what I meant. I was just testing you. 8.5. All right, so that's a weaker base. Okay, good. Any questions on this before I go to the next one?
Yeah, Professor, I just wanted to ask, my initial thought on this question was that you could just do that the pH is equal to pKa. Could you just quickly explain why that's not possible?
Okay, good point. All right, so pH equals pKa. What does that mean? This is a derivation of the Henderson-Hasselbeck equation, meaning for this to be true, the ratio of the conjugate base, so A minus, over the conjugate acid has to be equal to 1. At the equivalence point, we don't have this. We don't have the same number or the same concentration of conjugate base and weak acid. All of the weak acid is gone. So at the equivalence point, HA is 0. And the Henderson-Hasselbeck falls into dissolution. We can't use it. But this represents the pH equals the pKa. That represents what we call the half equivalence point. And that makes sense because what the half equivalence point means is when half of the weak acid concentration is converted into conjugate base. So if you have 1, you will then have 0.5 and 0.5. 0.5 of weak acid, 0.5 of conjugate base. If that's the case, this ratio would be 1, the conjugate base divided by the weak acid. Therefore, the log would be 0, and then your pH would equal your pKa. That's only true at the half equivalence point. So that's why that's true. But at the equivalence point, you cannot use Henderson-Hasselbeck. Does that make sense?
Yeah, I was thinking in terms of acid and base and not acid and conjugate base.
Right,
Sorry.
exactly. Okay, that's a very good question. Those are things that are very easily confused. So it's good that you asked that. Okay, so I'm going to erase this. I need a more powerful laptop. I'll get myself a present because it's like lagging when I try to erase things. I've had this for over year and a half now. It's good. It does the job. I have 8th gen i7. Does the job. Okay, so the part C. So calculate the pH of the solution after the addition of 0.0286 moles of NaOH. Now we have an excess amount of moles. So we can go directly and cut to the chase of how many moles of NaOH are in excess after we neutralize the weak acid. So 0.0286 minus our number of moles of acetic acid, 0.0179. And what is that going to be equal? It's going to be moles NaOH, moles of HA. So can anyone solve this for me? .0107. 0.0107. No, it's okay. Don't apologize. All right. So that number looks familiar. That's how much NaOH we added originally. But the problem is completely different. They did that on purpose. Just to try to confuse you. Now, this is the number of moles of, I'll call it active NaOH. So it's active because it's not neutralizing any acid. It destroys the buffer. So initially, even though this is a buffer, we have at some point in time we have weak acid in its conjugate base. That's a buffer. But now the buffer is destroyed because we have an excess of NaOH beyond the buffer capacity. So this excess NaOH can be used to directly solve for the POH and the pH. So the POH, since it's a strong base and it'll completely dissociate, will have negative log of 0.0107, which I imagine this would be a low number. So can anyone calculate that for me? And the pH will be 14 minus it. And we have 1.97, that makes sense, 1.97 as the POH, and that means the pH is going to be 12.03, which is very basic, and that makes sense.